Okay, so today I'm going to be going over the Exam 3 review. This is the review that is posted on the course website, not the Canvas page. So, yeah, you can find this at math1522.unm.edu or whatever it is. But I think I'm just going to go through all these problems. There are a lot of problems on this review, and there are a few problems that just say to go over like 8 sample problems from the textbook. I am not going to be going over that many problems for each of those sections. That would be like a ridiculous amount of problems at the end, but I did pick a few problems from those sections that I can cover. So, problem 1 just asks, what does the limit as k goes to infinity of a sub k being equal to L mean? What does it mean to say this? Well, it just means that the terms of the sequence can be made arbitrarily close to L, and when we take k to be sufficiently large as we go to infinity, we'll be approaching that value. And something we went over in class, but is not necessarily, is this means that for all epsilon greater than 0, there exists a natural number n such that for all k greater than or equal to n, the distance between a sub k and L must be less than epsilon. But just say sequence can be made arbitrarily close to L. That is sufficient. Okay, problem 2 asks, what does it mean for the sum from k equals 1 to infinity of a sub k to equal L? What does this mean? Well, if we think about, this idea of partial sums, we would have that the limit as n goes to infinity of s sub n, or I call this little n, so we'll call this little n, equals L, and this is true if and only if the series sums up to some finite number. So this is convergence in a more general language. Okay. So this says converges specifically to L when we have that the limit as n goes to infinity of the partial sums goes to that number L. Okay, let's look at problem 3. This problem 3 asks, assume this sum of a sub k equals L. What is limit as k goes to infinity of a sub k? And what is limit as n goes to infinity of s sub n, where they give us s sub n is of course the discrete sum from k equals 1 to n of our sequence. Okay, so since the series a sub k converges, we know this from the last problem, since it equals L, so converges to L, we know that its partial sums, s sub n, form a convergent sequence with the following limit. Moreover, the individual terms themselves actually tend to 0. And this was in your textbook when we were first learning about sequences in series, this difference between the successive partial sum terms. Okay. So if s sub n goes to L, then we can do some basic algebra with these limits. So we'd have the limit as n goes to infinity of a sub n would just be the limit as n goes to infinity of s sub n minus s sub n minus 1. This is just the limit of S sub n minus the limit of S sub n minus 1. S sub n and S sub n minus 1 must both go to L, so we end up with L minus L. So the limit goes to 0. So the limit as AK, or the limit as k goes to infinity. The limit is k goes to infinity of a sub k equals 0. Okay. Let's go to a different page. Problem 4 says, given the sequence a sub k equals 1 over 2 to the k, sketch a plot of the sequence, sketch a plot of the sequence s sub n, where that's the partial sums, and then find a sub k. So the sequence a sub k is a decreasing geometric sequence, right? 1 over 2 to the k. And, you know, the first term would be 1/2, 1/4, a sub 3 is 1/8, on, and our a sub k term is 1/2 to the kth power, which just goes to 0. So if we were to plot this, we would just put a bunch of discrete points that we could call, in this case, k and a sub k. It's the input and output. And they would have each step. They would reduce by half each step. And approximately, they would get smaller and smaller and smaller and be bounded to eventually go to 0. Okay, but for part B, so we want to sketch a plot of the sequence S sub n. So S sub n is our partial sum of 1 over 2 to the power of k. Also, hopefully everyone's okay with me writing this as 1/2 to the power of k, right? If we distributed this, we'd have 1 to the k over 2 to the k, which is just 1 over 2 to the k, which is what we started with. So that's why I'm writing it as this, just so it's in a more recognizable form. Okay, so this would be, we'll just use the, right, this is a geometric sequence, so we'll just use the geometric sum formula with a ratio of r being 1/2. So we'd have 1/2 times 1 minus 1/2 to the n over 1 minus 1/2. And this is just 1 minus 1/2 to the n. So now the point in this case would be n and then our S sub n, our sequence of partial sums, and it would increase monotonically. So S1 equals 1/2, and it would increase towards some horizontal asymptote at y equals 1. So whatever this asymptote is up here, we would have monotonic increasing up to this asymptote. Okay, now part C wants us to find the series represented by the sequence. So we're looking at what is this. Okay, well, r is 1/2, which is less than 1. So this converges by the geometric series test. So our series is, I keep saying, holy shit, I'm gonna lose my mind. I keep saying series and it activates my fucking assistant or whatever, the Siri on my iPad. So this is k equals 1 to infinity, and we know this is 1/2 to the k power. Okay, so again, we use a geometric sum formula, but this time we're not considering a discrete sum, so we don't need n terms. So we have 1/2 over 1 minus 1/2, which is just 1. So this series sums to 1 and it converges for 1/2 less than 1. If it feels like I'm kind of going through these problems fast, I think of these first few problems as more of like precursor problems or sort of broad overview problems. So I just sort of want to get through them fast. That way we can get to the more difficult problems. Okay, problem 5 asks, what is a telescoping series? I'm not going to go over this too much. A telescoping series is just a series whose terms can be written as differences of each other. So if the sequence can be written in the form bn minus bn plus 1, we call that an alternating series. Of course, this is a sequence, so when we sum it, it becomes the alternating series. So then, our partial sum would be which would be equivalent to saying this. And an example that we looked at, earlier in the semester, it was on one of your quizzes, was a series from 1 to infinity of 1 over n times n plus 1. We could rewrite this, if you remember, from partial fractions as 1 over n minus 1 over n plus 1. Then we considered its partial sum, which we could expand as 1 minus 1/2 plus positive 1/2 minus 1/3 plus on and on and on up to 1 over n, big N, over 1 minus n plus 1. And we made the argument that, okay, these terms will cancel, which implies that if we kept going in this direction, this would eventually cancel with whatever term is here. So all we're left with is 1 minus 1 over n plus 1. We shoved this back into to see if it converges, we want to take the limit of this. So the limit is capital N goes to infinity of S sub n equals the limit of 1 minus 1 over n plus 1. This goes to 0, so it's just 1. Okay. So that's a telescoping series. I think there's more examples later too that we'll go over. All right. Problem 6 says, consider the geometric series the following. So k equals k sub 1 to infinity of r to the kth power. For which r values does the series converge or diverge? Give 2 specific examples of converging geometric series, one starting at k1 equals 0, another starting at k1 not equals 0. Okay, I'm kind of just going to blow through this. I don't want to spend too much time on it, but this is just a more general case of our convergence condition. So in this case, we keep hitting my mic, hold on. So using our sum formula from the geometric series, we could find that this is equivalent to r to the k sub 1 power over 1 minus r. So for an edge case, if r equals 1, the terms are all 1, so we'd say the series diverges. If r would equal -1, the partial sums would actually end up alternating, so it would diverge because its limit wouldn't exist. But let's look at an example like this. So let's take r to be 1/3, and we'll consider k1 to just be 0. So we just have the sum from k equals 0 to infinity of 1/3 to the kth power, which would be just 1 over 1 minus 1 over 3, which is 3/2. And we could let's take k1 to be 2, which is fine, it's not equal to 0. And we'll let r be 1/2. So this would be from 2 to infinity of 1/2 to the kth power equals 1/2 squared over 1 minus 1/2. This gives us 1/4 over 1/2. So this is just 1/2, which is of course less than 1. I guess the only thing to look out for is that don't try to use 1 over 1 minus r regardless of the starting index. So for like k sub 1 not equal to 0, we need to include that factor r to the k sub 1 powered that's up here. Okay, I think that's all I want to say about this problem. Problem 7, for which values of p does the p series converge? Convergence of p is greater than 1 and divergence of p is less than or equal to 1. Right, we've seen this. We did a justification a while ago when we were doing the integral test. That's not necessary though in this case. All right, problem 8 asks, what is an absolutely convergent series? What is a conditionally converging series? Give an example of each. In okay, we'll just write this down so we remember. If the absolute value of an, the series of the absolute value of an converges, then the original series itself is absolutely convergent. All right, we've talked about this a bunch. If this diverges, then we say it's conditionally convergent, which I'll just abbreviate as C dot C. Okay, I'm not going to give an example of this, but I will. I'll just try to make up one. Like negative 1 to the n over n squared would be an example, right? If we took the absolute value, we'd have the series of 1 over n squared, which would be a p series with p equals 2. That converges. Negative 1 to the n over n cubed. Anything in those kind of forms will work. Okay, let's move on to problem 9. These are the fill in the blanks, so I'll sort of just run through what the solutions are. So part A says, a series with terms tending to 0 blank converge. This may converge. A necessary condition for the series to converge is that the terms must go to 0, but this alone doesn't guarantee convergence. So we call this, in the math world, we say this is necessary but not sufficient. Okay. B says a series that converges blank have terms that tend to 0. The answer is must. If the series an converges, then an must go to 0. That's the term test for divergence. C says if a series diverges and the terms blank not tend to 0, the answer is may not tend to 0. A divergent series can have terms that don't tend to 0, which forces divergence, but it can also have a sub n going to 0 and still diverge. An example of this would be like the harmonic series, like 1 over n, right? Its terms would go to 0 from the limit, but that series diverges by the p-series test. All right, D says if a series diverges and the divergence test blank succeed in proving the divergence, the answer is may. The divergence test succeeds when the limit of a sub n does not equal 0, it proves divergence. But if the limit of a sub n equals 0, then the test is inconclusive and we have to use something else. Part E says if the sum from n equals 10 to infinity of a sub n diverges, then the sum from n equals 1000 to infinity of a sub n blank diverge. So the answer is must. Removing finitely many terms, i.e. going from n equals 10 to n equals 1000, does not change the convergence or divergence of the series, right? And this makes intuitive sense, hopefully. Infinity is not something we can reach. So if we can show that that series converges for all these tests that sum up to infinity, then changing our starting point doesn't matter at all. Okay, F says if the sum from n equals 10 to infinity of a sub n converges, then the sum from n equals 10 to infinity of the absolute value of a sub n blank converge. So the answer to this is may. It may converge. Convergence of a sub n does not force absolute convergence. Again, if we had like negative 1 the n minus 1 over n, that would spit out the harmonic series when we took the absolute value, which diverges. So the answer to this is may. And finally, letter G says if the sum from n equals 10 to infinity of the absolute value of a sub n converges, then the sum from n equals 10 to infinity of a sub n must converge is the answer. Of course, if something is absolutely convergent, then by definition it is also just convergent. Okay, problem 10, I am skipping. These are a bunch of true-false questions in your textbook. You can go over those if you'd like, but I think they reinforce these primary ideas anyway. Okay, problem 11. This says determine whether the sequence converges or diverges. There's like 8 problems. We're going to be going over problems like this anyways for the actual examples. All right. Now, let's look at, where's my paper? Okay, let's look at a couple examples from problem 11. So these are in your textbook and I don't know, or chapter 11 in your textbook. At the end, I think there's a review section called exercises. But let's look at like a sub n equals n cubed over 1 plus n squared. Well, to show if this converges or diverges, this is a sequence, not a series. We just want the limit as n goes to infinity. So let's just look at what that is. This can be written as n cubed over n squared times 1 plus 1 over n squared. I just factor that n squared to the denominator. Of course, you don't have to follow this method if you don't like. All right, so this gives us n over 1 plus 1 over n squared. This is going to go to 0, we know. And so this whole thing is going to go to infinity. So an diverges by definition. Okay. These problems are all pretty easy, just solving limits, but like part B, we're given a sub n equals n sine n over n squared plus 1. We can make a sort of squeeze theorem argument. So we'd have n sine n over n squared plus 1. This would be less than or equal to n over n squared plus 1. So if we just ignore the sign value, and then this would in turn be less than 1 over n if we somehow extracted a 1 over n from this n over n squared plus 1 term. And as n goes to infinity, these terms go to 0. So a sub n would go to 0 as well. Okay. Problem 12. And again, there's a bunch of examples like this in this part in the book. Again, I'm not going to be going over all 8 examples in this part because we're going to be getting a bunch of examples later. But it boils down to just showing the limit, right? A sequence converges if its limit exists and exists as a real number. And if its limit does not exist or it goes to infinity or negative infinity, we say the series diverges. So problem 12 is similar, chapter 11 review, exercise 11 through 22, but this time we're determining whether the series converge or diverge. So I wrote down a couple that I wanted to go over. So this is 12, let's call it A. So the series from n equals 1 to infinity of n squared plus 1 over n cubed plus 1. Okay, so we have an is n squared plus 1 and n cubed plus 1. Let's do a limit comparison test on this one. This is a good candidate. So I'm going to pick my bn to be 1 over n, which we can extract out of this equation, of course. So now for the limit comparison test, we need to know the limit as n goes to infinity of the ratio between these two sequences. So this will give us the limit of n squared plus 1 divided by n cubed plus 1 divided by 1 over n, which is just the limit as n goes to infinity of, take the reciprocal, this will become n times n squared plus 1 over n cubed plus 1. And this is just the limits of n cubed plus n over n cubed plus 1. And this is, of course, once we multiply this n into the parentheses, that's what we get. Okay, so let's divide everything by n cubed. It's a classic way of solving limits. So this will give us n cubed divided by n cubed, which is just 1, plus n divided by n cubed will be 1 over n squared. N cubed divided by n cubed, 1 again, and then this will be 1 over n cubed. These terms go to 0 when n goes to infinity, so we're just left with 1 over 1, which is just 1. So now we have to remember with the limit comparison test what we're doing. We picked Bn to be 1 over n. This series diverges, right? This is a harmonic series, 1 over n. So since the series of b sub n diverges and the limit comparison constant is 1, which is in our interval, from 0 to infinity, the given series diverges by the limit comparison test because this term that we picked diverges. So our original series diverges by limit comparison test. And now one thing I want you to keep in mind while you're doing these problems is, we really want you to be methodical in the way you solve these problems. We want to see all your work in a logical workflow. This is sort of your first time doing proofs, I'll say in air quotes. Rather than solving an equation, we're asking you to sort of make a justification. So it's nice. Khalid's going to want to see, a nice logical flow of work and putting things in nice, simple paragraphs. And don't feel bad or feel wrong if you're using a lot of words, just like English words. That is very much expected when you're doing proofs like this because you need to use words to justify certain things. In this case, we're just taking a limit, so it isn't that crazy. But as we do some other tests, we might need to make some more justifications. Okay, that's problem 12. Let's look at another one here. I want to pick... And this is, again, from the examples that's in your textbook for problem 12. So the series from 1 to infinity of n cubed over 5 to the n power. Okay. This is a pretty good example. So this is a perfect ratio test candidate. Anytime you have, a general exponential, that kind of looks like a delta, hold on, 5 to the n. Anytime you have sort of this general exponential and even polynomial terms, this is a really good time to use the ratio test. Or anytime. The ratio test works a lot of the time. So we want this ratio, right? And we consider it absolute values. I'm going to drop the absolute value bars. Hopefully everybody's, comfortable with the fact that this is always positive. So, this would be a negative, but I'm just going to ignore the absolute value terms and just slap them on at the end. We'll just say that. So a sub n plus 1 will give us n plus 1 cubed over 5 to the n plus 1. We'll take the reciprocal right away. This would be 5 to the n over n cubed. This is just n plus 1 cubed times 5 to the n over, I can rewrite this 5 to the n times 5 to the first power times n cubed. These will cancel. And we're just left with this, we have this 1/5 down here. I'm going to pull it out. Times n plus 1 cubed over n cubed. Okay. And we can rewrite this as 1/5 times 1 plus 1 over n cubed. Okay, now we're, this whole time we want to consider its limit for the ratio test. So this limit goes to 1/5. Right, this goes to 0. We'd have 1 times 1/5. So this just equals 1/5, which is in fact less than 1. So we say the series AN is absolutely convergent by the ratio test. Okay. And we could do yeah, this is a good example too. So this is also same problem, 12. This is one of the exercises. So we're given AN equals the natural logarithm of n over 3n plus 1. And we want to show that this series converges or diverges. So we're given AN, but we're considering this as a series. But this is a perfect problem where we can use the divergence test by just simply taking the limit of a sub n. So the limit as n goes to infinity. The limit as n goes to infinity of a sub n is the limit of ln of n over 3n plus 1. Now this limit's a little daunting, but let's remember some basic limit rules for logarithms. We can actually pull the logarithm out and just consider the limit of the inside thing. So we can rewrite it as this. ln of the limit as n goes to infinity of n over 3n plus 1. This is a lot less daunting. This limit goes to 1/3, right? We could show that by L'Hopital's rule. So we just end up with ln of 1/3. This is not equal to 0. Therefore, the series diverges by nth term divergence test. Or just writing divergence test is equivalently acceptable. Okay, so tip, if you see a series with a logarithm in it like this, this is a good candidate to try the divergence test, because essentially we're just interested in finding the limit of this inside thing here. And if that limit looks like it might not equal 0, then I would recommend just doing this. It'll save a lot of hard work, because this might be kind of difficult to show using other methods because of this natural logarithm. But we can just take the limit and get our answer that way. Okay, let's move on to problem 13. So this is again in chapter 11, review problems, exercises 23 through 26. Determine whether the series converges absolutely, conditionally, or diverges. So we have 13, A. So let's look at the series from n equals 1 to infinity of -1 to the n minus 1, n to the minus 1 over 3. Okay, let's let an be -1 to the n minus 1, n to the -1 over 3, and let's pick bn to be just n to the -1 over 3. Okay, b sub n is greater than 0, and we want b sub n plus 1 less than or equal to b sub n, and we want b sub n to go to 0, right? We're using an alternating series test. Now, this is just equivalent to this, right? This alternating, when you take the absolute value, this alternating term would disappear, and we're just left with this. Don't confuse the negative sign up here for it somehow being positive after the absolute value. Remember, we can rewrite this as 1 over n to the 1/3. And this series diverges by p series, right? Because we have 1/3, which is less than or equal to 1. So b sub n, I guess we specify the sum of b sub n, right? Series are sums of sequences, diverges with p equals 1/3. Therefore, the original series, the whole thing, is only conditionally convergent. Conditionally convergent. Right? Because by alternating series test, something in this series does not converge. So we say it's conditionally convergent. Okay, let's look at another problem from this part. And I'm trying to pull up the textbook parts. Okay. Let's look at the series from n equals 1 to infinity of -1 to the n plus 1, 3 to the n, all over 2 to the 2n plus 1. So a little bit more involved, but let's, oops. All right. And we'll let this be equal to a sub n, of course. This whole thing specifically, ignoring the sum. So this is a good candidate for the ratio test. So we'll look at, and this gives us, after we take reciprocals, well, I guess let's make a simplification first to make things a little easier. This 2 to the 2n plus 1 could be a little tricky to work with, so this can be written as 2 times 4 to the n. Yep. And you can see that we'd get the same thing if you distributed. So this means that the absolute value of a sub n, which we need for the ratio test, is just 1/2 n plus 1 times 3 over 4 to the power of n. Okay, now that we have this, we'll set up a ratio test. A sub n plus 1 over a sub n. So this will be 1/2 n plus 2, because we're adding 1, times 3/4 to the n plus 1 power, all over 1/2 times n plus 1 times 3/4 to the n power. So this simplifies to these 1/2s go away, these 3/4 go away, so we're left with n plus 2 over n plus 1 times one of these copies of 3/4 is collected. Right, and this is because these will go away, these will go away, and then this is 3/4 to the n times 3/4 to the first over 3 over 4 to the n. These go away, so we're just left with 3/4. That's why that shows up here. Okay, so this is equal to 3/4, which is less than 1. So the series is absolutely convergent. By the ratio test. To make sure you guys are specifying that on your exam. Okay, let's look at another one, and here's the work, I guess. All right. Let's look at the sum from n equals 1 to infinity of -1 to the n minus 1 times n to the minus 3. This is a very nice series to work with. This is just the same as -1 to the n minus 1 over n cubed. Then I don't need to do really any work. I know that the absolute value is just this series, 1 over n cubed, and p equals 3, which is greater than 1. So this series is absolutely convergent by the p series, or by the p series test. Yeah. So a sub n is absolutely convergent with p equal to 3. Very straightforward problem. Okay, now let's look at one that sort of requires just making a little argument. So we have a series from n equals 2 to infinity of -1 to the n times the square root of n all over the natural logarithm of n. Okay. Now, right, we want to start at 2 because if we start at 1, we'd have ln of 1, which is 0. We can't divide by 0. It's undefined. So let's make an argument using the absolute value of a sub n. So we just want to consider everything but the alternating term. So we have root n over ln of n. Now, the argument I'm actually going to make is just a divergence test where we just look at the limit. So we want the limit as n goes to infinity of, I'm just looking at the absolute value of a sub n. So this is the limit as n goes to infinity of square root of n over natural logarithm of n. Now you could go through and use L'Hopital's rule if you'd like, but this limit goes to infinity and there's some nice intuition that we could use. This ln of n is going to grow a lot different than square root of n. So when we plug in large values of n, we'd see that it goes to infinity because the numerator would get very large versus the denominator would get very tiny. So therefore diverges by divergence test. So not a too involved problem, but it's, it kind of quizzes you on understanding the ratios of these different kinds of functions and what their growth implies about the limits. But if you don't want to make that argument, you could, of course, brute force this and use L'Hopital's rule, because we know the derivative of square root of n, that'd be 1 over 2 root n, and then the derivative of ln of n would be 1 over n. And you can make an algebraic argument from there. Okay, now I think we have one more. No, that was the last solution for this part. Okay. Problem 14. Again, this is in chapter 11, the review section, exercises 27 through 29. It says, find the sum of the series. Okay, we haven't done this too much on quizzes, but we know sums of series for series that have known sums. This isn't something we can do for every series, but let's look at, so this is problem 14. Series from n equals 1 to infinity of -3 to the n minus 1 over 2 to the 3n. Okay, so this is actually a geometric series, kind of hidden. And our first term, a sub 1 would be -3 to the 1 minus 1, which is just 0, over 2 to the 3n, n is 1, so it's just 2/3. So this is just 1/8. And our common ratio is actually given by a sub n plus 1 over a sub n. So we can compute this. This would just be -3 to the n over 2 to the 3 times n plus 1. Right, and this becomes n because n minus 1 plus 1 would just be -1 plus 1, which is 0, so we just have n. And then this is all divided by, let's see, we'd have -3 to the n minus 1. And then this would be over 2 to the 3n. We can take reciprocals, and we get that this is simply just -3 over 2 cubed. So this is just -3 over 8. And our ratio in this case is n less than 1, 3/8 specifically. Right, and these are equivalent statements. The absolute value of -3/8 is equivalent to the absolute value of 3/8. So we know the sum converges and it's geometric, so our series our series can, holy shit, this, I have to figure out how to turn this Siri off or something. I never use this. Whatever. We could use the geometric formula, which is coefficient a1 over 1 minus r. We found a1, our first term, to be 1 over 8. And our common ratio is minus 3/8. So this comes out to, what would this be? We'd have 1/8 over 11/8. So this just gives us 1 over 11. And that's the sum of our series. So the one thing to keep track of, again, a common error is forgetting that the series starts at n equals 1, which means we need to compute a sub 1 correctly, then use the formula a sub 1 over 1 minus r, not just 1 over 1 minus r. Here's the zoomed out version so you can see all the work. Okay, and let's look at a good telescoping series problem. So we have sum from n equals 1 to infinity of 1 over n times n plus 3. Now, we can use partial fractions on this. So our numerator is 1. A, we multiply it by the denominator we don't have, so n plus 3 plus b times n. So this can be written as, what can we factor? We can have a plus b times n plus 3a. This is all equal to 1. And we'll find our coefficients this way. So a plus b equals 0. 3a equals 1 when n equals 0. So a is 1/3. And b is just minus 1/3 in that case. So we can rewrite 1 over n times n plus 3 as 1/3 times 1 over n minus 1 over n plus 3. So now we're looking at, this series. And now we can use, our telescoping knowledge to find a sum for this. So geometric series and telescoping series are two series that have known sums if we can find their partial sums. So again, the process is we set up our partial sum. This is a sum from little n equals 1 to big N of, in this case, I want that 1/3 out in front. We're going to put it in our simplified form. So this will be 1 over n minus 1 over n plus 3. Okay, this is 1/3 times, when we start plugging in terms, starting at 1, we'd get 1 plus 1/2 plus 1/3 minus 1 over n plus 1. This would go on 1 over n plus 2 minus 1 over n plus 3. Okay, so, and now we want to we want to take the limit as n goes to infinity. So we're letting n go to infinity. And what do we get? All of these terms are going to go to 0, right? And these constant terms are not going to be touched. So we should just have that the limit as n goes to infinity is 1/3 times 1 plus 1/2 plus 1/3. And this would be 1/3 plus 1/6 plus 1/9. So this would be like 1/3 times 11 over 6. So 11 over 18. And so that's the sum of our telescoping series. So it's the same idea as that one that we did like in our quiz earlier, but the cancellation is a little different. But that's the sum for that. Okay, let's go on to problem 15 now. So problem 15 says show, and forgive me for not writing down all the problem statements, but it'd be a lot of writing. But so show that the series, we'll put the series down, k equals 1 to infinity of minus 1 to the k minus 1 over k cubed. We want to show that this converges, and then we're asked how many terms are needed. How many terms are needed to approximate the sum with error less than 10 to the minus 3. Okay, these are problems that you definitely want to make sure you practice. We're going to be using the alternating remainder theorem, which is a very powerful theorem, but it's not too hard. So we essentially want to know, we want to show that it converges. If it doesn't converge, we can't even use the theorem. This is easy to do. So I'm going to just show this by absolute convergence. I'm not going to even use the alternating series test. So this just becomes the sum for 1 over k cubed. P equals 3, which is greater than 1. We know that this is absolute convergent then by P series. Okay, so it converges. So we're trying to show or determine how many terms, capital N, are needed so that the n-term partial sum, S sub n, approximates the full sum, which goes up to infinity, and we want the error between the difference of those two to be less than 10 to the minus 3. 10 to the minus 3. So let's define our original sum as calling it big S, and this is our sum that goes from 1 to infinity. This is our actual series over k cubed. And then our partial sum is simply just a discrete version of this. Instead of going up to infinity, we'll just go up to n. And this all stays the same. Okay, so the remainder, or error, they're the same thing, but the terms are intertwined, is given by r sub n being the difference between your true series and your approximated one from your partial sums. So, and I guess we want absolute values on these. We're just looking at how well our partial sum actually approximates our original series. That's all we're doing. So, algebraically, we want to calculate this. We want to know what this difference is. So, like, how do we subtract these two series from each other? Well, there's a nice intuition, and it's this idea of a tail of a series. So if this series goes to infinity and this series goes to n, this is obviously much larger, infinitely larger. If we take that infinitely large series and subtract an n large series from it, what is left? Well, the n will get absorbed by that infinity. Infinity's larger, the n will completely go to 0. So all we're left with is everything that comes after n and goes up to infinity. So we write this now, instead of from k equals 1 to n, that n got chopped off. So we're only looking at everything after n, and we write that as n plus 1, right? The first thing after n, and we take this up to infinity. And then nothing changes in here. This is still minus 1 of the k minus 1 over k cubed. So that's the intuition for how to actually form this r sub n. Okay, so now we'll actually use the remainder theorem. So for some alternating series in a form like this, an alternating term negative 1 to the k times some term b sub k, we assume b sub k is greater than 0. And in the alternating series test, we want b sub k to be greater than 0. And we want b sub k plus 1 to be less than or equal to b sub k. So eventually decreasing is how we say this. And then we want the limit of b sub k to go to 0 as k gets large. So we know the series converges. We know what our partial sum is. We know what our remainder is. So we have this following theorem. We want the absolute value of r sub n to be less than or equal to b sub n plus 1. So we're taking k to be n. And we don't need to mention the next part. That's not even in your textbook. Okay, so we just really want to look at this inequality. What does this give us? Well, this would be 1 over, we're letting k be n plus 1. So instead of 1 over k cubed that we chose b sub k to be, we're looking at 1 over n plus 1 cubed. Okay, and now from here we just need to solve this. This is our r sub n. That's what we're trying to show is less than 10 to the minus 3. So we want to set 1 over n plus 1 cubed being less than 10 to the minus 3. And we'll solve this. So we can divide on both sides. So this will mean that we have n plus 1 cubed, which is greater than 1,000. Okay, and that's because, right, 10 cubed is 1,000. When we divide, we flip the sign of the inequality, and this will become positive because we're taking its reciprocal and then flipping it to the other side. Okay, so where are we at now? We have that n plus 1 cubed is greater than 1,000. So this is what we're trying to satisfy. So if n just equals 10, what do we get? We have 10 plus 1 cubed equals 11 cubed, which is greater than 1,000. So we can stop at least 10. So what we should write is that we want n plus 1 to either be greater than or equal to 11. If it satisfies that, then it'll be greater than 1,000. And in other words, this just means that we want n itself to be greater than 10. And this is really our answer. So n greater than or equal to 10 will satisfy this inequality. And now what we'll do is sort of just, put everything back in if we were to consider the actual alternating term. So again, we sub k for n plus 1. And just some nice algebra we can do is that this would become negative 1 to the k minus 1, but k is n plus 1, so n plus 1 minus 1 over k cubed, but k is n plus 1, so n plus 1 cubed. This is the same as negative 1 over negative 1 to the n over n plus 1 cubed. Okay, so how do we formulate this? So taking n to be 10 gives the partial sum evaluated at n equals 10. We write it as s sub 10 is strictly less than our original sum that goes up to infinity, which is itself less than s sub 10. So we bound it between these two values, and we add this term here. So s is strictly greater than the partial sum evaluated at 10, but it's less than the partial sum evaluated at 10 plus this new term 1 over 11 cubed, which we got from solving that inequality. So in other words, we'd have s sub 10 plus 1 over 11 cubed. This is all we're looking at. Okay, and I guess we could say the error bound satisfies strictly 1 over 11 cubed is less than 10 to the minus 3. And this is our solution for this problem. So show that it converges. In this case, we can use absolute convergence, but you could just use the alternating series test. Set up this remainder, which is just the difference between think of it as the difference between your true solution and your approximated solution. Then we can set up r sub n as using this, this intuition of cutting off part of the series and then looking at the tail. So we're looking at everything after n plus 1. And then we satisfy the conditions for the alternating series test, but we're considering the remainder now. So we sub all k for n plus 1, and then we can solve this inequality. And then we can just sort of tie it all back together at the end and go from, this form here after we divided in our inequality back to what, the problem statement was. Okay. let's see what's next. Problem 16. This problem 16 is chapter 11 review exercises 38. Okay, so this is just a ratio test practice, but let's go through it. So A, we have the series n equals 1 to infinity of n to the n power over 2n factorial. And we want to show that this series is convergent. So, of course, we choose an to be n to the n over 2n factorial. And we'll just shove this through the ratio test. So this will be an plus 1 over an. So this will give us n plus 1 to the n plus 1 over 2n plus 2 factorial over n to the n over 2n factorial. Make sure you use parentheses with these factorials, right? We generally don't write these when we have something more than just n factorial without parentheses. So make sure you're always including parentheses, just a thing to keep in mind. We could take the reciprocal. All right, what do we get? We'd have n plus 1 over 2n plus 2 factorial times n to the n. So this just comes out to n plus 1 to the n plus 1 over n to the n. And times 2n factorial over 2n plus 2 factorial. Just write it as this. Okay, so let's just work on simplifying each part. So let's look at just this part, n plus 1 to the n plus 1 over n to the n. So we can split this up as n plus 1 times 1 plus 1 over n. We did this trick earlier. And we can split up, let's look at the factorial terms now, is what I'm trying to say, over 2n plus 2 factorial. We use the fact that like n plus 1 factorial is equal to n plus 1 times n factorial. It's one of your identities that you should know. And how would this simplify? Let's see. This would just be 1 in the numerator over 2n plus 2 times 2n plus 1. We get a copy because we're looking at 2n plus 2. Okay, so we go back to our ratio. What is this really then? This is n plus 1 times 1 plus 1 over n to the n over 2n plus 2 times 2n plus 1. So this is just 1 plus 1 over n to the n over 2 times 2n plus 1. Okay, so a little bit more involved, you know, maybe an example like this difficult won't be on your exam, but we can use a pretty cool fact now. So we ended up deriving this algebraically, but this is actually a common limit. So we want the limit as n goes to infinity, of course, of an plus 1 over an. Absolute values, but these are all positive, so I just forgot them. So we're looking at the limit of this and the limit of this separately. So the limit of this we saw earlier in the semester, this is actually e. Specifically, this is e to the first power, which is just e. If you don't remember how to do that limit, I would recommend going back a few homeworks and looking at that limit. But we can use logarithms to take that n out of the exponent and then do all the logarithmic limit work to get to this solution. But so we have e, and our denominator goes to infinity, right? 2 times 2n plus 1 will just go to infinity. E is a constant, so this whole thing just goes to 0, which is less than 1. So our series is absolutely convergent by the ratio test. So, it's an involved example, but, the algebra might be a little, annoying. But it's the same process as what we've been doing. Just, look over my work and see if you can follow along like that. And then we invoke this limit to get e. I think on the exam, if you see something in this form, it's fine if you just put e to the 1 or e squared. I don't think Khalid would care if you invoke that because we've already done it in the past. But if you do get to that point, you forget how to do it, I would recommend reviewing logarithmic differentiation just so you have a method to always solve this kind of limits. Okay. Now 16 asks another part. So part B, where is it at? Okay. So part B is a little vague. Holy shit. Okay. We want to deduce that the limit as n goes to infinity of n to the n over 2n factorial equals 0. So, they're just trying to reinforce this idea of growth. And by deduce, they mean just sort of make an argument by words. I don't think a problem like this is going to show up on your exams, but for the solution, we'll just talk through it. So we know that a necessary condition for a series to converge is that the terms must go to 0. This series converges. And right, we said earlier that that's a necessary condition, but it's not sufficient. We need to show other things. However, we just showed that this series converges by the ratio test. It converges absolutely. So to argue that this limit goes to 0, we just say since the series in A converges absolutely, then by definition, this must go to 0. That's the whole problem. Alternatively, I guess you could make a ratio estimate, which would look something like trying to solve this. But in this case, we already had that, part A prerequisite, and we found that the series converged. Okay, problem 17. We want to determine the radius and interval of convergence of the following power series. So we're looking at problem 17, and we're looking at the power series n equals 1 up to infinity of 3 to the n times x plus 4 to the n all over root n. Okay, so let's just use a ratio test with an being equal to all of that. So we'll set it up. This is going to be 3 to the n plus 1 times the absolute value of x plus 4 to the n plus 1 over square root of n plus 1 times our reciprocal is going to give us root n over 3 to the n absolute value of x plus 4 to the n. Okay. So this is just 3 times the absolute value of x plus 4 times the square root of n over n plus 1. So now we're just looking at the limit. We want to consider the limit as n goes to infinity for the ratio test. In terms of power series, right, this term is not touched by the limits. We're using this to find our radius of convergence. So we're just looking at the limit of this. And we could divide by n. This whole thing would go to 1. So we'll get that it's just 3 times x plus 4 times 1. So we just have 3 times the absolute value of x plus 4. Now, with our ratio test, we know that a series is absolutely convergent by the ratio test if L being the limit of the ratio equals L and is less than 1. So this thing here is our limit solution, so we want this whole thing to be less than 1. Now, to find our radius, we just want to isolate our x plus 4 term. So this would be the absolute value of x plus 4 less than 1 over 3. Therefore, our radius of convergence is just 1/3. Okay, very nice. So now we can set up the candidate interval for our interval. So this would be negative 1/3 less than x plus 4 less than 1/3. I want to subtract 4 on both sides. So we're left with negative 13 over 3 less than x less than negative 11 over 3. And so this is what we can call our candidate interval. You know, our interval of convergence is definitely going to be this, but we don't know if it converges or diverges at these endpoints. So we'll check them. So when x equals minus 13 over 3, let's see, we'd get x plus 4 equals minus 1/3. And a sub n would be 3 to the n minus 1/3 of the n over square root of n, which would just be negative 1 to the n over square root of n. This is equivalent to negative 1 to the n over n to the 1/2. We can see pretty quickly that though this has a p series form over n to the 1/2, this is an alternating series. Right, so we can actually use the alternating series test, and this converges. Converges by alternating series test, where we'd let bn be the absolute value of an, which would be 1 over square root of n. Then we'd want to check, bn plus 1 less than bn, which would be 1 over root n plus 1 less than or equal to 1 over root n. And then we know its limit goes to 0 because we'd have a constant over infinity. So these check, and so it converges by the alternating series test. So our endpoint minus 13 over 3 is included in our interval. Okay, now let's check at the other endpoint. X equals negative 11 over 3. So we have x plus 4 equals 1/3. And a sub n is going to be 3 to the n times 1/3 to the n over root n, which is just 1 over root n. Now, this gives us a p series, 1 over n to the 1/2, with p equals 1/2, which is less than 1. So it diverges by the p series test. Diverges p series. So what does this mean about the problem? We know our radius is 1/3, and our interval of convergence is then our endpoint minus 13 over 3 included because it converged, and then up to negative 11 over 3, but not including negative 11 over 3. And so this is the process you should go about finding the radius and interval of convergence. Setting up, and if you forget, right, we're looking at essentially letting L be the limit as n goes to infinity of a n plus 1 over a n times x minus a. And we want this to be less than 1 for it to be absolutely convergent. And this x minus a, of course, comes from just the general form of our power series, which if we go back and look, our series is in this form, right? It's just sort of hidden. And in this case, our a was minus 4 because we had x plus 4 to the n. So this is the process. Just recognize power series, use ratio test, and make sure you multiply by this term, and then solve the inequality and test the endpoints. That's it. Okay, let's move on. Okay. Problem 18, so this is chapter 11 review. Exercises 40 to 43, find the radius and interval of convergence of the power series. So I'll go over like 2 of these, but we're going to be doing the same process just now with some other power series. So let's look at this example. This is a pretty good one. So this is problem 18, and we're looking at the series from n equals 1 to infinity of negative 1 to the n times x to the n over n squared times 5 to the n. Okay, so we're going to use ratio test. So a sub n plus 1, a sub n. So we're going to have, and I really do want to keep my absolute values this time because of these alternating terms. So negative 1 to the n plus 1 times x to the n plus 1 over n plus 1 squared times 5 to the n plus 1. And then this is all over negative 1 to the n. Let's see, x to the n over n squared 5 to the n. Absolute value. Okay, so this is just the absolute value of x to the n plus 1 over n plus 1 squared 5 to the n plus 1 times n squared 5 to the n over the absolute value of x to the n after our reciprocals. So this just simplifies to n squared over n plus 1 squared times absolute value of x over 5. Right, we pulled this 5 out from right here, canceling these terms and having a 5 to the 1 left over. Okay, so let's look at the limit now. So we're looking at the limit of n squared over n plus 1 squared times absolute value of x over 5. Okay, what does this limit evaluate to? Again, we don't touch the term with x in it. That's just considered a constant term as far as the limit goes. So this whole thing would go to 1. And we could use L'Hopital's on that. So we just have 1 times absolute value of x over 5. So really we're just left with the x, absolute value of x over 5. And in order to be absolutely convergent, we need to set this less than 1. You take the reciprocal of 5. And this just comes down to we're looking at absolute value of x less than 5. So this means our radius of convergence is r equals 5. Okay. And our candidate interval is negative 5 to 5. And we want to check the endpoints. So let's do that. So at x equals, let's see, positive 5 first. We're looking at, a sub n evaluated at 5. This is just negative 1 to the n times 5 to the n over n squared 5 to the n. This is just negative 1 to the n over n squared. Okay, and this converges, All right, we're looking at this series now. Converges by alternating series test. I'm trying to save a little bit of time because there's so many problems, but go through, pick Bn to be absolute value, so 1 over n squared, and look at Bn plus 1, so 1 over n plus 1 squared versus 1 over n squared. Their limit goes to 0. Show that. Okay, and now at x equals -5, we'd have a(n) of -5, which is -1 to the n, -5 to the n, over n squared, 5 to the n, which is just 1 over n squared. And this is also convergence, but we can make an easier argument just using p series. So convergence with p equals 2, which is greater than 1. So our radius is 5, and our interval of convergence is -5 to 5, all included. All right. And that is the solution to this problem. So, as always, just go through the ratio test, solve the inequality, test the endpoints. Okay, now, is there another problem I want to do from here? Yeah, like this is a good example. The series from n equals 1 to infinity of 2 to the n, x minus 2 to the n, over n plus 2 factorial. Okay, and we want to find the radius and interval of convergence. So again, we always let an equal all of this, and let's set up the ratio. So this is just 2 to the n plus 1 times absolute value of x minus 2 to the n plus 1 power, all over n plus 3 factorial, and then we'll multiply by the reciprocal, so this will give us n plus 2 factorial, and 2 to the n times the absolute value of x minus 2 to the n. Okay, so we can see from some nice simplification that we're going to get rid of one of these. And likewise, we're going to get rid of a 2 to the n and just be left with a 2 to the first power. And we can use the fact that n plus 1 factorial is n plus 1 times n factorial. So we get, this will just come out to, let me see here, it should be 2 x minus 2 over just n plus 3, because we'd lose one of those factorial terms by using that identity. Okay, and so really we're looking at the limit as n goes to infinity of let's just even pull this out just to make it even more clear. We'll pull out this 2 times the absolute value of x minus 2 times the limit as n goes to infinity of 1 over n plus 3. Okay, so this limit goes to 0. This whole thing's going to go to 0, so this whole limit is going to go to 0. Now, and right, we're calling our limit this capital L. L is equal to 0, which is less than 1 for every single x, as long as x is a real number. So this means the series converges for all x. So our radius of convergence is infinity, and our interval is all real numbers, negative infinity to infinity. And of course, we never use the brackets saying we're including those endpoints, because there is no endpoints, right? Infinity is not something we can travel to. But this is a good example of a series that converges for all real values, similar to like e to the x, which is in a similar form, x to the n over n factorial. You've seen probably in class and homework that converges for all real values. And similarly, so does this. So let's move on to problem 19. Chapter 11 review, concept check, problem 911. I'm skipping this one. This is what we've been doing, but these are some extra problems. So let's go straight to problem 20. 20. All right, 20 says, let f of x be the following series. So f of x is the sum from n equals 1 to infinity, x to the n over n squared. And we're asked to find series representations for f prime, f double prime, and then find the intervals of convergence for f, f prime, and f double prime. Okay, so this is a pretty fun problem, I think. So we're given this series f of x. So to find the radius and interval of convergence for f, we'll just run through the ratio test. So we pick an, right, to be x to the n over n squared. So our an plus 1 over an is just absolute value x to the n plus 1 over, this would become n plus 1 squared. We'll multiply by the reciprocal, which is n squared, over just absolute value, that looks weird, absolute value x to the n power. Okay, we can make some sweeping cancellations. So all we're left with is just n squared over n plus 1 squared times the absolute value of x. And we're looking at the limit, of course, as n goes to infinity. So this will go to 1. Again, I think we saw this limit in another problem or something similar. But it goes to 1. You can show that by L'Hopital's rule. So we just have 1 times absolute value of x. So we're just left with the absolute value of x after the limit. And we, of course, want this to be less than 1. So our candidate interval is -1 to 1. Oops. And we'll test the endpoints. So we'll write now that I'll do this notation. The radius of f is equal to 1. Just so we can distinguish between f and f prime and f double prime. Okay, so let's look at the endpoints. So when x equals +1, we just get 1 over n squared. This converges. P series. P equals 2, greater than 1. Okay, we're good at this endpoint. X equals -1. We get -1 over n squared. This converges absolutely. We don't even need to use an alternating series. Converges absolutely. Again, when we do the absolute convergence test, we would use the P series argument here. So both of our endpoints converge. So the radius for f is 1. And the interval of convergence for f, again, I'll write it like this, is -1 to 1 included. Okay, so that's the first part of the problem done. Pretty simple. They already gave us the power series, so we're just looking at the ratio test. Now we want to find the radius and interval for f prime, so we need to actually find out what f prime is. And to do this, we will just differentiate our series term by term. So this will become the sum from n equals 1 to infinity d dx of x to the n over n squared, which is just the sum from n equals 1 to infinity of n times x to the n minus 1. Again, we're just using power rule here. Very simple. And then this n squared just doesn't change. Okay, get rid of an n. So f prime of x has a power series representation. N equals 1 to infinity of just x to the n minus 1 over n. Okay, and so now we're looking at finding the radius of convergence for this. And we're just going to go through the exact same process that we were doing. So we'll do a ratio test on this. So let's see, we'd have, okay, I guess I should make a jump, right? All right, let's just go through the ratio test. We'll just do it. Better to be detailed. So this will be x to the n plus 1 minus 1 will just be x to the n. Or x to the n minus 1 plus 1 will be just n plus 0. So n over n plus 1 times the reciprocal will be n times x to the n minus 1. This will be x to the n times n over n plus 1 times x to the n times x to the minus 1 times x to the minus 1. Okay, and when we take the limit, all we're left with is just, right, we can bring this x up. This limit will go to 1. Again, either divide by powers of n or use L'Hopital's rule. And so we're just looking at the absolute value of x again being less than 1. So in this case, our radius of f prime is just 1. So we'll keep track of that. And then we have the candidate interval, -1, absolute value of x to 1. So let's test at the endpoints. We have x equals 1. This gives us the harmonic series. This spits out 1 over n. This diverges. P equals 1, right? It's harmonic. So we failed at this endpoint. Check x equals -1. And this would give us the series -1 to the, what would this be? Oh, just n minus 1 over n. Okay, now this actually converges. This is a harmonic, but it's an alternating series. In the form of a harmonic, we call this an alternating harmonic. And we can just, hold on, we could say alternating harmonic. We can just make a similar argument, just let Bn equals 1 over n, then set up, 1 over n plus 1 less than or equal to 1 over n. 1 over n goes to 0 and we take its limit. So all the stuff that we need is, still normally defined for the alternating series test. So we converge at this endpoint. So what do we have? Our radius for f prime is 1, and our interval of convergence is -1 to 1, written as such. So brackets at -1 and parentheses at +1. Okay, now we'll do f double prime. So we want the radius and interval for f double prime. So we're going to differentiate the series again. So we have the sum from n equals 1 to infinity of d dx x to the n minus 1 over n. This is just the series from n equals 1 to infinity of n minus 1 over n times, this becomes x to the n minus 2. Okay, now the n equals 1 term is 0 because n minus 1 over n equals 0. So we can actually start at n equals 2, and we don't need to change anything about the inside of our series. This is just a simple observation. So we just say n equals 2 to infinity, and it's the same series times x to the n minus 2. And I guess we should be circling these. These are answers too. The question wants the power series representation as well as, just the interval and radius. So let's make sure we go back and circle or power series, which is fine. All right. So again, from ratio test, we do the same process. We want x less than 1. These power series usually give us the same result here. So at x equals 1, what do we get? We have n minus 1 over n times 1 to the n minus 2. This just goes to 1, which is not equal to 0. Now, all I did here is use the divergence test. So I took the limit as n1 to infinity of this. And again, if you see a sequence that you think its limit does not equal 0, try the divergence test first, just taking the limits, because it's a very quick way to show that something diverges if it passes. So this goes to 1, which is not equal to 0. So it diverges by, again, we can just call this divergence test. So we failed at this endpoint. Now let's look at x equals minus 1. Okay, so let's also use the term test again. So the absolute value of n minus 1 over n, and this would now be negative 1 to the n minus 2. This is just now, this would just go to 1, so we just have n minus 1 over n. We're looking at this limit. We already saw in the last problem that this goes to 1. So diverges by the exact same argument, the divergence test. If you would like, of course, you can run through an alternating series argument or some other argument, but I would recommend using this argument for it. So what do we have? Our radius of f double prime is 1, and our interval of convergence of f double prime is negative 1 to 1, not including both endpoints. Okay. And that's this whole problem. So I guess just things to finish up, this problem, like reminders, I'll zoom out. Use the ratio test on a to the n equals x to the n over n squared to get r equals 1. Check the endpoints at x equals plus or minus 1 to find your interval of convergence. And then to go for f and f double, or f prime and f double prime, just differentiate term by term to find f prime, and then differentiate f prime to find f double prime. Okay, now problem 21 is chapter 11 review. This is also a true or false quiz. I'm not going to be going over this, but let's look at problem 22 now. So problem 22 says, use series to show that cosh x is greater than 1 plus 1 half x squared for all x. So, more of a novel problem, but let's look at it. So, cosh x, I guess we're trying to show, I'll write down the problem statement. Show that cosh x, which is, the hyperbolic cosine, is greater than 1 plus 1 half x squared for all x. So you've seen hyperbolic cosine and sine and hyperbolic tangent, and you know that they're defined by e to the x. And we have nice power series for e to the x, x to the n over n factorial. So there's a very common power series that arises for cosh x based off of the power series for e to the x, and that is that cosh x is sum from k equals 0. I'm going to write in terms of k instead of n to infinity of x to the 2k over 2k factorial. Okay. And if we looked at a few terms, our first term would be 1 plus, we'd have x squared over 2 factorial plus x to the 4th over 4 factorial plus x to the 6th over 6 factorial, on and on and on. So it's the numerator and denominator are doubling. The numerator is doubling its exponents, and the denominator is doubling its factorial terms. So the way to approach this is let's just split off the first two terms So, right, we're given that we want to show that cosh x is greater than 1 plus 1 half x squared. And if we notice that the first two terms of this series are, in fact, 1 plus 1 half x squared. Right, I wrote that as x squared over 2 factorial. 2 factorial is 2. We can pull that 2 out as a 1 half. And it looks like this. So to solve this problem, we're going to split off the first two terms. So we'll let cosh x be these first two terms, this quadratic part, if you will. And then plus, and now we'll fill in, you know, this goes on and on and on for infinity, so we'll just fill in that gap by putting the concise sum version. Okay, so this will be the sum from k equals 2 to infinity. We're doing that because we're omitting the first two terms from this series. So instead of starting at 0, we don't want to start at 0. We want to start after the first two terms, so we start at k equals 2. So make sure we pay attention to that. X to the 2k over 2k factorial. And this is actually, this would be called the remainder. The remainder, r of x. So the argument that we can make is that every term in the remainder is non-negative, at least for all real numbers x, and even powers. And at least one of these terms is positive whenever x does not equal 0. So what we can formulate is that cosh x is these quadratic parts, 1 plus 1 half x squared, plus this series we're calling r of x, the remainder, which itself is greater than just the first two terms on their own. And that probably makes intuitive sense, right? These are both equal, but when we add this will be a non-zero, this will be a non-negative, non-zero number. So it's obviously going to, this whole sum is going to spit out something greater than this. And that's the argument. That's all it is, really. Again, not like a super strict problem, but definitely good practice and gives good intuition about splitting off series. This is a very common practice in a lot of problems, so it's good to see it. Okay, let's do problem 23 now. So this problem has 3 parts. Let's see. All right, part A, we're given f of x equals sine of x. We're asked to find the first 5 non-zero terms of the Taylor series for f, centered about a equals pi over 6. So we'll note that down. Okay, so we've seen, right, a Taylor series is a power series. Where these coefficients have this closed formula being the nth derivative at a over n factorial. That's how you've been introduced to Taylor series. So let's just use, we're just going to use the standard formula for the power series of sine of x. So, and we don't even really need the sum formula. What we really need is the derivatives, right? The problem asks us to find the first 5 non-zero terms of the Taylor series. We know that in the Taylor series, we need the derivatives. They show up right here. So the first five non-zero terms means that we want f all the way through the 4th derivative of f. Think of counting in indexes more than anything. So f is just sine of x. F prime is cosine of x. F double prime is negative sine of x. F triple prime is negative cosine of x. And then the 4th derivative is derivative negative cosine, which is just positive sine of x. And this is nice, right? We have this sort of like circular behavior where everything loops back to sine of x eventually. You know, we like trig functions for that. And then they specifically give us that we're centered about a equals pi over 6. So we need to know what these derivatives are at those values, including the function. We also need to know what f is at pi over 6. So f of a, where a is pi over 6, would be sine of pi over 6 is just 1/2. F prime of a, would be looking at cosine of pi over 6, and this is root 3 over 2. And once we have these first two values, we actually have all the other values, right? They're just going to alternate between negative and positive signs. So f double prime of a is given by negative 1/2. F triple prime of a is just negative root 3 over 2. And then our fourth derivative, evaluated at a equals pi over 6, is just positive 1/2. Again, we loop back. Okay, now we'll form the Taylor series. So, right, we have f of a, and then it'll be f prime of a times x minus a, f double prime of a times x minus a squared over 2 factorial, right? We know the pattern. So f of a is just 1/2 plus f prime of a is root 3 over 2 times x minus a to the first power over 1 factorial, which is just 1, minus f double prime is minus 1/2. So we have minus 1/2 times x minus a squared over 2 factorial. And then f triple prime is negative root 3 over 2. So this is minus root 3 over 2 times x minus a cubed over 3 factorial. And then finally, fourth derivative is just 1/2, so plus 1/2 times x minus a to the fourth over 4 factorial. And this would go on and on and on. But this is an acceptable answer. This is the first 5 non-zero terms of the Taylor series for sine of x centered about a equals pi over 6. Okay, so really we just need the derivatives, and then you need to know the form of a Taylor series, right? How to actually form a Taylor series based on the derivatives. Okay, now part B just wants us to find they want us to give P2 of x, where P2 of x is the Taylor polynomial of degree 2 for f, again centered about a equals pi over 6. So nothing changes there. Now this is super easy. We already have the first 5 non-zero terms of our Taylor series. So our degree 2 Taylor polynomial is just going to be a truncation of that series expansion. So specifically what we'd like to have is the first 3 terms. Again, we're counting it as like 0, 1, 2 versus 1, 2, 3. So this will need f, which is 1/2, plus root 3 over 2 times x minus a, and then minus 1 over 4. I'm just simplifying that factorial term, that 2 factorial, x minus a squared, where a is equal to pi over 6. And so you can go back, you could go in and plug in pi over 6 for a, and that would be an even more concise version. But that's, as long as you have a Taylor series expansion, you can find the Taylor polynomial like that. Okay, so this part's easy. Now part C is a little bit more involved. We're going to be using Taylor's inequality. So C says, find an upper bound for the error, which is the error, again, error and remainder, same thing, defined as the difference between our true function, which is f of x, versus our approximation of that true function, which is the truncation of our Taylor series, which is our second degree Taylor polynomial. So we want the difference between f of x and P2 of x. And they give us that it should be on the interval 0 to pi over 3. Hopefully everybody can agree that pi over 6 is in fact an element of that interval, right? Because pi over 6 is less than pi over 3. So we want to bound the error when approximating f of x equals sine of x on the interval 0 to pi over 3 by the degree 2 Taylor polynomial about a equals pi over 6, as given in part A and B. So let's just consider a more general form of our second degree Taylor polynomial, and hopefully you can agree with me. This is just f of a plus f prime of a, x minus a, plus f double prime of a 2 factorial times x minus a squared. Right? And this is what we had earlier, but we did all this work earlier. We know that we evaluated f at a equals pi over 6 to be 1/2. But we'll consider this general form. So the remainder now is specifically in respect to the second degree Taylor polynomials. So instead of Rn, we're looking specifically at R2, and this is a function of x. So equals the difference between f of x minus p2 of x. Okay, so Taylor's inequality from your book tells us that if the absolute value of the n+1 derivative of f evaluated at x is less than or equal to some number that we're calling capital M for all x, where the absolute value of x minus a is less than or equal to some value that we don't know yet, but we're calling little d, then for all x in that range, we should specify, we have the following inequality that Rn of x, the absolute value, is less than or equal to this number m over n+1 factorial times the absolute value of x minus a to the n+1 power. Okay, so we're just going to apply this with n equals 2 since we're using the second degree Taylor polynomial. So we'll now just use this formula. So, okay, let's remember our functions. F of x is sine of x, f prime is cosine, then it becomes f double prime is negative sine, negative cosine, and then back to sine. So we want to look at the n+1 derivative, right, from our statement and our theorem. N is 2 because we're using the second degree Taylor polynomial. So we're really looking at the 2 plus 1 derivative. So we're interested in the third derivative of f. So we want the third derivative of f evaluated at x, absolute value, right? We need to satisfy, we need to somehow satisfy this condition before we can jump into this formula. So this is the third derivative of f evaluated at x. This is just the absolute value of negative cosine of x. Equivalently, this is just the absolute value of cosine of x. Hopefully that makes sense to everyone, right? The absolute value of negative cosine is just positive cosine, or the absolute value of positive cosine. And I'm going to bound this by 1, less than or equal to 1. And hopefully, again, everyone can see this, right? Cosine oscillates its range between -1 to 1 for infinity, right? If we think back to trig, that cosine wave will go between -1 and 1. So we can set it less than or equal to 1. Less than if it is -1, or equal to if it is 1, but it can't be greater than. Okay, so this is how we pick our m. This thing right here is our m. Similar to how we find the radius of convergence from the inequality, our m will be chosen from here. So we have m equals 1. We'll hold that as an aside. Okay. Now we need to find out what this lowercase d is. So we want to choose d such that the entire interval, which in this case is 0 to pi over 3, lies within this inequality that we have. So a is pi over 6, and that's the midpoint of the interval, in fact, right? 0 to pi over 3, pi over 6 is actually the midpoint of this interval. So the furthest point from a equals pi over 6 are the endpoints, 0 and pi over 3. So we want to look at the absolute value of 0 minus pi over 6. This is just going to spit out pi over 6. And then similarly, we want to look at the other endpoint, pi over 3 minus a, where a is pi over 6. And this is just pi over 6. So both of these spit out pi over 6. It's in our range. So that is our d. We choose our little d now. All right. Our lowercase d to be pi over 6. So Yes, this is how you choose m, and you choose lowercase d. So just think back to the theorem in the book. We need to satisfy this inequality. In this case, we were using cosine, right? So the range that we're talking about is -1 to 1. If this was sine of x, you could use that too, -1 to 1. But then for other functions, you'd have to find the range of that function to make sure you either find it manually, or you might be able to just see it by just looking at the function. And then for lowercase d, we look at this inequality and we consider the interval that we're given, and we want to find out where the center, a equals pi over 6, actually sits relative to that interval. And then we can just test the endpoints. So in this case, 0 and pi over 3. And now we have a value for lowercase d being pi over 6. Okay, so now we can actually jump straight into the formula. So let's collect everything. We're looking at R2 of x, because we're looking at the second degree Taylor polynomial. And this is just the difference between f of x and our second degree Taylor polynomial. And Taylor's inequality tells us that this is less than or equal to m over 2 plus 1, right? We have n plus 1, n is 2, so I'm just going to write it as 2 plus 1 factorial times x minus a to the n plus 1, n is 2 again, so I'm going to write this as 2 plus 1. So this just comes out to 1 over 3 factorial times x minus a cubed, right? Where this 1 is equal to m, and then 2 plus 1 is just 3 factorial. Very straightforward. So since on the interval that we're given is 0 to pi over 3, we know that this is true, that x minus a is less than or equal to d. In other words, x minus a is less than or equal to pi over 6. We found lowercase d to be pi over 6. So since that's true, then the uniform bound on the whole interval is just given by f of x minus p2 of x, which is less than 1 over 3 factorial, which we found, times just pi over 6. And this is cubed. And this is the answer, but this also simplifies to pi cubed over 1296. So this is our answer. The question was, find an upper bound for the error on the interval 0 to pi over 3. This is our bound. Pi cubed over 1296. Okay, so general thoughts, just consider everything you're given. We need to know the derivatives, and we want to consider the remainder when n equals, in this case, 2, because we were asked earlier to find the second degree Taylor polynomial. But that can change if you were asked to find the fifth degree Taylor polynomial or something. You would apply the theorem that way. And then we use the theorem from the textbook, and we find m by checking the range, and we find lowercase d by seeing where that a value sits inside of our given interval. And then we plug everything back into the inequality at the end so that we can actually get a bound. Okay, that is 23. So let's move on to 24. All right, so 24, we're asked to find the power series for the following functions and give their radius and interval of convergence. So we have a bunch of them, so let's just try to go through it. So 24, we're given f of x equals 2 over 3 minus x. I'm going to write this as 2/3 times 1 over 1 minus x over 3. So this is 2/3, and now we can form the geometric sum, or the geometric power series, with our common ratio is x over 3 to the n. And we want to put that 2/3 into the series, so we treat it like a copy of that 3 in the denominator. So we'll have series from n equals 0 to infinity of 2 over 3 to the n plus 1 times x to the n. So this is our power series. Now I think for these problems, I am going to skip the part where I go through the radius and interval of convergence just because I think it'll take way too much time. Hopefully those examples from before will give you a good idea, but basically what we do have is that you should get that x is less than 3, so the radius is 3. And it turns out that the interval of convergence is -3 to 3. So it diverges at both endpoints. And so I recommend you go through and do that practice just to make sure you are all good on finding radius and interval. But the real bulk of the problem is this. This is our power series for f of x equals 2 over 3 minus x. Okay, let's look at part B, which is f of x equals, well, let's write it. B f of x equals x over 2x squared plus 1. So a little bit more involved, but not too bad. So we'll just write this as x times 1 over, let's rearrange this just so it looks more like the form we want. All right, hopefully everybody can agree that this is equivalent. Now we can actually write this as x times 1 over 1 minus 2x squared. That way we're in the form of 1 over 1 minus x. So this is just the power series, or x times the power series specifically, n equals 0 to infinity. Our common ratio is -2x squared to the n. Now we can pull this x in, and I'm going to pull the -2 to the n out of that minus 2x squared to the n. So this will be the series from n equals 0 to infinity of -2 to the n, which we pulled out. And then that x to the 2n becomes x to the 2n plus 1 after we throw that x in. So x to the 2n plus 1. And this is our power series for f of x. Now, similarly, I'll let you go through the work, but you should get to that 2x squared is less than 1, right? And this means that the absolute value of x must be less than 1 over root 2, just from some basic algebra. So you test, so now your interval is -1 over root 2. It's 1 over root 2. And after testing at the endpoints, it turns out they both diverge. So your interval of convergence is -1 over root 2 to +1 over root 2. And your radius is just 1 over root 2. So, go through, see if you can do that on your own, and you should get that answer. That it diverges about the endpoints, and the radius is 1 over root 2. Okay, let's look at problem C now. And so we did this in class. This is a fun example of we got to differentiate then integrate. So we're looking at finding the power series of inverse tangent, or the arctangent of x. So we'll just go through the steps, right? The derivative of f prime of x, the derivative of f of x is f prime of x, which is, if you remember, the derivative of arctangent is 1 over 1 plus x squared. Let's rewrite this as 1 minus x squared. So this is the power series from n equals 0 to infinity of minus x squared to the n. So this is just n equals 0 to infinity. We'll pull out a -1 to the n, and then this becomes x to the 2n. Now, this is our power series for f prime of x, right? We want a power series for f of x. So to go from f prime to f, we integrate. We want the antiderivative. So I want to integrate this series x to the 2n with respect to x is what we're integrating. Again, we can pull the sum out of the integral. So we get that this is the sum from -infinity, or from 0 to infinity, of this -1 to the n doesn't get touched because we're integrating with respect to x. And then this x to the 2n becomes x to the 2n plus 1 over 2n plus 1. Okay. And this is our power series for f of x equals tan inverse of x. We have the convergence condition absolute value x less than or equal to 1. So we want to test at the endpoints, -1 to 1, and it turns out that it converges at both endpoints. I'm sure you can see a nice little alternating series argument if you'd like. So this is -1 to 1 included, and the radius is, of course, just 1. So, go through and try to get that. But as far as finding the power series for this goes, right, we're always trying to fit it into the form 1 over 1 minus x. So all these functions were already in an algebraic form, or at least in a form that could be just manipulated algebraically. But tan inverse of x, we can only think to ourselves, okay, is there any way I can turn tan inverse into something that kind of looks like 1 over 1 minus x? And then we access our toolbox and we say, okay, well, I know that the derivative is 1 over 1 plus x squared. And then we go from there. And just really remember, do not stop at this step after you get this power series. Remember, this is the power series for f prime. It's asked for f, so we have to go the other direction by integrating. And when we integrate, we don't lose, the radius stays the same for f prime, and f doesn't change. Okay, let's look at part D. So this is f of x equals x over 2 minus x squared. Okay. So this is a little bit of like an ugly factorization, but I'm going to just give you the factorization. So we have 1/4 times 1 over 1 minus x over 2, and then this thing is still squared. That kind of looks ugly. X over 2 squared, right? And so this 4 will cancel with that 2 in the denominator. So what we're looking at is 1/4 times the series, and it equals 0 to infinity of, in this case, we need an n plus 1 term because it's squared. So we want n plus 1 times, and then our common ratio of x over 2, and this is to the nth power. So we can pull this 1/4 in, and we'll get that this is the series from n equals 0 to infinity of n plus 1 over 2 to the n plus 2, and times this x to the n plus 1 term. Now, so this is our power series for f of x. Similarly, we have x is less than 2, so our boundary is actually -2 to 2, so these are our endpoints. So our radius is 2, and it turns out the interval of convergence is -2 to 2. And it diverges at both endpoints. Okay. Now let's look at problem E. This is kind of a fun problem going in a reverse direction from what we might have seen. So we're given E is f of x equals the integral from 0 to x of t over 1 minus t to the 8th dt. Now, for the love of God, please do not, if something like this showed up on your exam, try and solve this integral. Do not solve this integral as is, right? We're talking about power series, so there's obviously going to be some kind of manipulation. So we have a t in the numerator. This is fine. We can just pull this out. Let's just look at 1 over, right? We'll just pull the t out here. 1 over 1 minus t to the 8th. This is already in the form of our power series, so this is very nice. So this is t times the sum from, this time I'm going to call it k. I guess we should specify, right? Let's just look at, let's ignore this t for now. We'll just consider this. This would just be the sum from k equals 0 to infinity of just t to the 8k. Then we're given f of x is this integral of t over 1 minus t to the 8th dt. This is the integral of now this power series that we know. So I guess let's specify this. Let's pull this t out. I want it out. I want it inside the integral, sorry. 0 to the x, t times sum k equals 0 to infinity, t to the 8k dt. Now before we think about integrating anything, let's simplify this. We want to push this t into our series. So this becomes the integral from 0 to x, sum from k equals 0 to infinity. Now this will just become t to the 8k plus 1 because we just added a copy of t dt. Now we integrate after we found that power series. So we integrate term by term. This is simple enough. This will just be the series from k equals 0 to infinity of... Now, one thing I'd pay attention to, right? The integral they give us is not just an indefinite integral. They give us 0 to x. Now, this just means, and this is very nice, all this means is that we're swapping variables at the end. So we're in terms of t. When we integrate, we're going to now be in terms of x instead of t. And then this 0, it doesn't matter. The term will be 0. So after we integrate, we should have the series of x to the 8k. 8k plus 1 is 8k plus 2. And then by power rule, we divide by that 8k plus 2. So this is our power series. Make sure you're definitely going to get points docked off on the exam if you do not swap variables at the end. That's a clear thing outlined in the problem. So, Professor Khalid is going to want to see that you guys are tracking on that. Okay, so this problem is fairly straightforward. It's a little daunting at first because we have this integral, but really just isolate 1 over 1 minus t to the 8th. We know that power series, and then shove that t back in, and then we integrate that whole power series, which is then super trivial because, the power series is in terms of these, like t to the 8k, which we could just use the power rule on. Okay, so that's E, and did I go over? Yeah, okay. And let's do maybe one more from these. Oh, and I should specify, right, with this series, we'd be looking at x less than 1, and so your radius is 1, and the interval of convergence turns out to be -1 to 1, not included. So, again, as always, make sure you, and check if you can get to that on your own. Okay, I want to look at one more from these. Let's look at F. So, or I think I went through all of them, so this should be the last one, yeah. Okay, so F, we're given f of x equals x times sine of x squared. Okay, now whatever we do not differentiate, right? I know it, like when we had tan inverse, you might be thinking, oh, I need to take the derivative and then integrate that power series. No, you guys know a Taylor series now for sine of x. Yeah, you've been taught that in class with Taylor series. So we're just going to invoke that. So let's just ignore the x and just look at sine of x squared. We know the general Taylor series for this, but with the x squared term, it's just going to modify it slightly. So we're just going to have the power series now from n equals 0 to infinity. We have that alternating term. And then instead of 2n plus 1, we're going to have x to the 4n plus 2 over, and then this still stays the same in the denominator, 2n plus 1 factorial. So this is the power series for sine of x squared. We want x sine of x squared, and so now this is as simple as just shoving that x into the series. So it's n equals 0 to infinity, -1 to the n. This becomes x to the 4n plus 3 after we add that x in, over 2n plus 1 factorial. This doesn't change. Okay, so this is the power series for x sine of x squared. And super easy solution if you know that the power series for sine of x is -1 x to the 2n plus 1 over 2n plus 1 factorial. And I'm sure Khalid doesn't need you to derive that Taylor series like every time on the exam. You can just invoke it and use it. Now, you should check the radius on this is infinity, and the interval of convergence is all real numbers, negative infinity to infinity. So make sure you can get that. Okay, and that's problem 24. So let's look at problem 25. So, okay, so we're asked, find the power series for ln of 1 plus x squared about x equals 0. Use the resulting series to estimate the value of ln of 1.01 within 7 decimal places, 10 to the minus 7. Okay. Let's see here. We want to use the fact that ln of 1 plus x as a general power series. So if we just think of that x squared being a u, then this is just the power series from n equals 1 to infinity of negative 1 to the n plus 1 u to the n over n. And right, this converges for u less than 1. U is x squared, so this is really negative 1 to the n plus 1. Let's write this as just x to the 2n over n. So now it converges for x less than 1. Okay, this is our power series. This isn't that bad. So the radius is 1. And we're looking at our endpoints plus or minus 1. So we can check. We get an alternating harmonic. So we end up with, our interval is negative 1 to 1 included. Again, go through that work if you need to. Okay, now we have our setup really for this problem. Now, to estimate ln of 1.01 within 10 to the minus 7, we need to note that ln of 1.01 is equivalent. ln of 1.01 is equivalent to ln, it's equivalent to ln of 1 plus 0.1 squared. So essentially letting x equal 0.1, we get that ln of 1.01 is the series n equals 1 to infinity, negative 1 to the n plus 1 times 0.01. That's what happens after we square 0.1 over n, or to the n over n. Now, this is just calculator stuff. So this will be 0.01. Imagine we're expanding this series. That's all we're doing. 0.0001, right, over 2. And then this alternating sign, we're flipping signs. We start with a positive term, right, because it's negative 1 to the n plus 1. So we'd have negative 1 squared. All right, plus, this will be 0.000001 over 3, so on and so forth. So this is an alternating series with decreasing terms. So we can actually use the alternating series remainder theorem, where Rn satisfies that it's less than or equal to the next term, which is just to say that R sub n is less than or equal to b sub n plus 1. And the next term in this would be, we'd have the series 0.01, and that n, we now look at n plus 1 instead of little n. So this is n plus 1 over n is big n plus 1. So this. Now, let's take n equals 3. Okay. So the next term, this bn plus 1 term, would be 0.01 to the fourth over 4. This can be written as 10 to the minus 8th over 4. Or in scientific notation, this is 2.5 times 10 to the minus 9th, which is less than 10 to the 7th. And the problem, if you remember, asked us to estimate the value within 10 to the minus 7th. So 3 terms, letting n equals 3, is suffice. And so let's compute that 3 term to actually get our approximation. So ln of 1.01 is approximately, we should use 0.01 minus 0.001 or 0.0001 over 2 plus 0.000001 over 3. Okay, so we want the first 3 terms, so we stop here. So we're just looking at these. So this is our estimation. If you plug this into a calculator, I don't know if I plug this into the calculator right, but you'd get like 29,851 over 3 million, which is approximately like 0.0099 and like a bunch of other numbers. The number part isn't really the important part. Just make sure that you know to find the power series for that function. And then as far as estimating goes, you just want to use the alternating remainder theorem, at least in this case, because we have an alternating series. And all we're setting up is Rn less than Bn plus 1. So we're just looking at the next terms, and then the problem tells us specifically that it needs to be within 10 to the minus 7. So we could just test different values of n. I jumped straight to n equals 3 just to get to the point, but start at n equals 1. Obviously that's not it, 0.01. N equals 2, then go to n equals 3, and just make sure it satisfies this. And then you calculate the number of terms that this ends up satisfying. On a test, I'm sure you could just leave it like this. If he even gave you a problem like this, he's not going to expect you to do this at all in your head because you guys don't have access to calculators. But that is that problem. So let's now go to problem 26. Okay. So we want to use series to approximate the following integrals. So we have the integral for a is from 0 to 0.1 of 1 over 1 plus x to the 4th dx to within, they tell us 10 to the minus 7th again. Okay. Again, do not try to integrate this on its own. It's going to be written as 1 minus x to the 4th. So this ends up spitting out the power series, n equals 0 to infinity, negative 1 to the n, x to the 4n. Okay. Now we'll integrate term by term on the interval 0 to 0.1, and we know it's uniformly convergent on this interval, so we'll have the integral from 0 to 0.1 of 1 over 1 plus x to the 4th dx is equal to the sum from n equals 0 to infinity minus 1 to the n times the integral, right? We can pull that integral out of, or we can pull that sum out of the integral 0 to 0.1 x to the 4n dx. So this gives us the series n equals 0 to infinity negative 1 to the n of, this will give us 0.1 to the 4n plus 1 over 4n plus 1. Okay. Now, at this point, we can see that this is an alternating series again, with terms bn being 0.1 to the 4n plus 1 over 4n plus 1. So we're again going to use the alternating series remainder theorem. So we have Rn less than the next term, which we call bn plus 1, which would be 0.1 to the 4 times n plus 1 all over 4 times n plus 1 plus 1. So we're just replacing that little n with the next term, which is capital N plus 1. Okay. So we want to choose n, capital N, choose capital N, such that bn plus 1 is less than 10 to the minus 7. So again, we'll check. Let n equals 1. We get b2, right? Because we're looking at bn plus 1. If n is 1, then it's b1 plus 1, so we're really looking at b sub 2. This is 0.1 to the 9th power over 9. This is 10 to the minus 9th power over 9. And this is less than 10 to the minus 7th. So keeping terms n equals 0 and 1 suffices. So what's our approximation then? The integral from 0 to 0.1 of, I'm not going to rewrite the function again, we know what it is approximately 0.1 to the first power over 1 minus 0.1 to the 5th power over 5. Right, this is just the expansion of our series for 2 terms. And this gives us 1/10 minus 1 over 5 times 10 to the 4th. Again, if you had a calculator, this comes out to like 49,999 over 500,000, which is roughly 0.099 and a bunch of other numbers again. Again, if like the calculator, it doesn't matter too much, but this means that our error then is, of course, R1 less than or equal to 10 to the minus 9 over 9, which is less than 10 to the minus 7. So we've solved this problem. We found the approximation. So we can check B naught, B sub 0 equals 0.1. B1 is 0.1 to the 5th over 5, which is 10 to the minus 5 over 5. So they're decreasing. So the alternating remainder bound applies to this problem. Okay, so let's just go over what we did. We've seen integrals of a function and where we're asked to find the power series. We know now that, we just simplify the integrand into a power series, and then we integrate that series term by term. In this case, we're given actual definite bounds, 0 to 0.1, so we plug in those bounds into our power series. And then we use the alternating remainder theorem to actually find what that bound is and find our approximation. So we look at the next term, bn plus 1, and then we check values. I checked n equals 1, which satisfied our inequality immediately and gave an approximation. Okay. So let's look at this next integral. So this is part B of this problem. So we're estimating the integral from 0 to 1 of sine x over x dx to within 2 decimal places, so 10 to the minus 2. Okay, so, or within 10 to the minus 2. This integral is actually a very famous integral. I forget the name of it, but sine x over x, and it very famously, I think, doesn't have an analytical solution for the indefinite case, but we can approximate this with Taylor series. So what I want you to do is think that we know the power series for sine of x, so we'll pull the 1 over x out and just look at the power series for sine over x, and then when we put that x back in, it's going to modify our power series because we're adding that x term in. So what we end up getting is that sine x over x is the power series n equals 0 to infinity of negative 1 to the n x to the 2n over 2n plus 1 factorial. Go through the steps, make sure you can get this, but it's not really the focus of the problem, so I'm just going to jump straight to the power series for it. Okay, so now we'll integrate term by term. So the integral of the sum in this case is going to give us the series n equals 0 to infinity, negative 1 to the n, and this becomes times 1 over 2n plus 1 factorial times 2n plus 1. Okay, so this is also an alternating series with decreasing terms, bn. So to achieve an error less than 10 to the minus 2, we want to stop when the next term, bn plus 1, is less than 10 to the minus 2. So we'll just compute a few terms. So b sub 0 is 1 over 1 factorial times 1, just 1. b1 is 1 over 3 factorial times 3, which is 1 over 18. And this is approximately 5.5 times, times 10 to the minus 2. Okay. Now b sub 2 is 1 over 5 factorial times 5. This gives us 1 over 600, which is approximately 1.667 times 10 to the minus 3. Okay, so we've computed these terms, and b2 satisfies this. b2 is less than 10 to the minus 2. So taking two terms up to n equals 1 already guarantees a desired accuracy. So using three terms gives a tighter bound, so we can actually present this three-term approximation because we're looking at n plus 1. So let's do that. This means that our integral from 0 to 1 of sine x over x dx can be approximated as 1 minus 1 over 18 plus 1 over 600. And this comes out to 1,703 over 1,800, which is approximately 0.946111, on and on. Okay, and the alternating series error is bounded by the next term, so we can write R2 is less than Bn plus 1, n is 2, so this would be B sub 3, which would be 1 over 7 factorial times 7. This comes out to 1 over 35,280. Factorials grow really fast. This is approximately 2.84 times 10 to the minus 5, which is in fact less than 10 to the minus 2. Okay, so this is our approximation. And I guess the only remark I would have is that even the two-term sum, so 1 minus 1 over 18, is equivalent to 17 over 18, which is approximately 0.9444. And that would in fact satisfy to the 10 to the minus 2 accuracy, since its next term would be the one after 118, so 1 over 600, which is 0.001667, which is less than 0.01. Okay, so these are two really good examples. Definitely expect to probably have to use Taylor series to approximate something, either an integral or something of the sort. So make sure you look over these problems and reach out if you have questions on those. Okay, let's now use series to evaluate limits. So problem 27. We're given the limit as x approaches 0 of sine of x minus x plus 1/6 x cubed all over x to the 5th. Okay, so the goal is just, we like polynomials. These are very easy to find the limits of. We don't want the sine x, but I know that I can express the sine of x in some way that it has polynomial terms, and that's with the Taylor series. So that's the whole goal of this. So recall that sine of x has the Taylor series x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus on and on and on. Now, let's just simplify this a little bit. So this is equal to x minus, this would be x cubed over 6 plus x to the 5th over 120 minus x to the 7th. Oops. X to the 7th over 5040. Okay, so we obviously can't go up to infinity, so we're going to do just like a little trick kind of to solve this limit. So just looking at the numerator, we have sine x minus x plus 1/6 x cubed. This is our Taylor series sine of x, so x minus x cubed over 6 plus x to the 5th over 120 minus x to the 7th over 5040, on and on and on. And then what's left over is we're subtracting x from that and then adding 1/6 x cubed. So this is the numerator of our limit. So what happens here? A bunch of things cancel. This is actually just the same as saying, right, this would be x to the 5th over 120. If we distributed this, and minus x to the 7th over 5040. Right? These are going to go away, and these are going to go away. And we're just left with these. Those are kind of jarring lines. Let's just do this. So these terms cancel, and then all we're left with is these terms. So our numerator is actually just this. So we're looking at this, and we have to remember that this is just the numerator. Our denominator had this all divided by x to the 5th. And as x goes to 0, we just go to 1 over 120 from this limit. All right. I guess let's make sure we see what this does. This would become 1 over 120 minus x squared over 5040 as we lose these x terms. And this goes to 1 over 120 when x goes to 0. And so that's the solution to our limit using Taylor series. A thing that you should try to remember is that you don't want to stop the sine expansion at x cubed because that gives 0 over x to the 5th. You need the x to the 5th term to get the correct leading constant. Okay, let's look at another limit. Okay. So we now want to approximate the limit, or not approximate, we want to evaluate the limit as x goes to 0 of square root 1 plus x minus 1. What is this? Minus 1/2 x all over x squared again. Okay, so this problem uses something called the binomial Maclaurin series. And I don't think you're taught this in this class, but it is under review, so we'll go over it. But I don't remember this, but I'll give you the general form. And if you've taken a college algebra, you might have used this actually to find multiply, like if you had like x plus 1 to the 5th, you can use the binomial expansion to actually multiply those terms out without doing it by hand. So the binomial expansion is for a function 1 plus x to the alpha. Is given by the power series k equals 0 to infinity of, this is what's called a combination, this notation. This is not a vector or something. This is saying alpha choose k times x to the k. So it uses some, what's it called? Combinatorics. And so I'll give you the formula for the combination as well. So this is saying alpha choose k and this is written as, what would this be? This would be alpha factorial. I'm used to it with like n choose k or something, over k factorial times n, or n in this case is alpha, times alpha minus k all factorial. Okay, so basically we have, and we can kind of see why they want us to use this binomial theorem. Again, I'll just go through the solution, but probably don't worry too much about this problem. But it is very nice, and this is certainly a useful series. So, right, if the binomial series is in the form of a function 1 plus x to the alpha, this is actually what this is. Right, the square root of 1 plus x is equivalent to saying 1 plus x to the 1/2 power. So our alpha would be 1/2, so we'd have, we'd have 1 plus x to the 1/2. So this would be the series from k equals 0 to infinity of 1/2 choose k times x to the k. And so this is the series that they're invoking for this problem. But let's go through how we can approximate this limit. So assuming you knew how to find this power series, assuming you knew what this binomial series was, and you can find it, this has an expansion. So square root of 1 plus x has an expansion by the binomial Maclaurin series as 1 plus 1/2 x minus 1/8 x squared plus 1/16 x to the cube, or x cubed, sorry, minus 5 over 128 x to the 4th. Okay, so let's subtract, and then in our original limit we're given, right, it's minus 1 minus 1/2. So let's just subtract the 1 and positive 1/2 off of this. This will go away when we add those. So we're just given minus 1/8 x squared plus 1/16 x cubed minus 5 over 128 x to the 4th, so on and so forth. So now we divide everything by x squared, so our limit comes out to, or not the limit, but the function comes out to minus 1/8 plus 1/16 x minus 5 over 128 x squared, on and on and on. We're looking at the limit of this, obviously, as in this case x goes to 0. So these go to 0, these go to 0, and all we're left with is just minus 1/8. So this is the solution to our limit. So, you know, maybe I'm like not making, maybe you have seen this in class and I completely missed it. But even if you haven't, at least seeing what the formula for this series is, you can hopefully see how we applied the same process from last time. The trick of, it's like what we do with the telescoping series, where when we expand it, there are these terms that cancel, and simplify our limit to just purely these, like a polynomial. Okay, that is problem 27. So, let's look at 28, I guess. Okay, 28a says, find the function represented by the power series. This power series is n equals 2 to infinity, n times n minus 1, x to the n, and find its interval of convergence. Okay. So let's just start with what we know. Right, the sum from 0 to infinity of x to the n is given by 1 over 1 minus x. And let's differentiate this series term by term. So let's consider the derivative of this. This gives us 1 over 1 minus x squared. So use quotient rule or use chain rule, you'll get that. I guess we don't need that yet, sorry. When we differentiate this, we'll just get the series from n equals 1 to infinity n x to the n minus 1 just by the power rule. And this is equivalent to the function 1 over 1 minus x squared. We, yes, okay. So we took that derivative, and now we started with, where is it in our original problem? We need to multiply everything by x. So let's take series from n equals 1 to infinity of n x to the n. This gives us common ratio x, so x over 1 minus x squared. And let's differentiate again, and of course term by term is valid as long as absolute value of x is less than 1. So our series n equals 2 to infinity of n times n minus 1 x to the n minus 1 is equal to d dx of the function x over 1 minus x squared, which is equivalent to, again, we're gonna, like, you'd have to use quotient rule on this, but this would be 1 minus x squared minus x times 2 times 1 minus x times negative 1 all over 1 minus x to the 4th. And this is just, we can simplify this. It's 1 minus x squared plus 2x 1 minus x over 1 minus x to the 4th. Okay, now let's try to simplify the numerator if we can. So 1 minus x squared plus 2x times 1 minus x can be written as 1 minus 2x plus x squared plus 2x minus 2x squared. And this is just 1 minus x squared after simplifying. So our series, we started with n equals 2 to infinity, n times n minus 1, x to the n minus 1, equals 1 minus x squared over 1 minus x to the 4th. Okay, so now we just multiply by x to match the given powers. So I want x times 1 minus x squared and over 1 minus x to the 4th. This will give me 2x squared over 1 minus x cubed. Okay, and so this is the function represented by the power series n times n minus 1 x to the n minus 1. So, okay, and then interval of convergence. Again, I'm going to let you go and do this on your own, but I'll give you that we want x less than 1, so our radius should be 1. And we have n points, negative 1 and 1, and it turns out that the interval, they diverge at both endpoints. So see if you can get to that. But now, what are we doing with this problem exactly? So essentially, we're given a power series now, and we're asked to find the function. So we're kind of going backwards. We've been usually just doing, like, we're given a function, we say find a power series. And we know from doing all those problems that a common technique is to differentiate and then integrate. So in this problem, we're assuming that the series is already in some kind of derivative form. And we're using that to, and we're using the basic geometric series, x to the n, and differentiating it until we eventually get to something that looks like what we have. And as we're doing those derivatives, we then analyze what the function representation is for that current power series. So we have n times x to the n minus 1 at first after we differentiate, which is 1 over 1 minus x squared. And then we do it again, and we end up with x over 1 minus x squared, or that's after we multiply x in. But we differentiate again, and we have to use this ugly quotient rule, but we end up with n times n minus 1 x to the n minus 1. And we can simplify the numerator and denominator, and that gives us our function that's represented by the power series. Okay, and then as far as finding interval and radius and convergence, it's just the standard after that because we're already given the power series. So let's do part B. N times n minus 1. This is another binomial thing, so I don't know how helpful this is going to be, but we'll go over it. Okay. So evaluate the sum of the series n equals 2, n times n minus 1 over 2 to the n. So we're going to evaluate this series at x equals 1/2 using the closed form that we found in A. So this will be the series n equals 2 to infinity, n times n minus 1 over 2 to the n. This is the series from n equals 2 to infinity of n times n minus 1 times 1/2 to the n power. Okay, so this is, remember, we know from what our function representation is, we can find this to be 2x squared over 1 minus x cubed, and we're evaluating that at x equals 1/2. That's what this notation is. Hopefully you remember from Calc 2, or not Calc 2, from like Calc 1, when we use this big vertical bar, it's a shorthand for saying evaluated from x equals 1 over 2 in this case, or at 1 over 2. Okay, so this is just then 2 times 1/2 squared over 1 minus 1/2 cubed. This just comes out to 2 times 1/4 over 1/2 cubed, which is 1/2 over 1/8, which is just 8 divided by 2, so 4. Okay, so this is how we do this. We just use the form that we found in part A to rewrite it. And because we're interested in this problem, this whole problem, 28a and b, is really asking us to look at the function represented by the power series, versus we're used to evaluating power series rather than the function itself. But now we're looking at a power series and saying what function does that represent. Okay, let's go to problem. Okay, problem 29 is the same process as like problem 15 or whatever we did earlier using the Taylor theorem. So I'm not going to go over this just for the sake of time because this video is way too long. Let's just do problem 30 and call it a day. Okay, I am not going to write this problem down because it is too long to write, but let's go through it. Okay, when a voltage capital V is applied to a series circuit consisting of a resistor R and an inductor L, the current at time t is given by the formula I equal to V over R times 1 minus e to the minus RT over L. Part A wants us to find the Taylor series for I centered at R equals 0. So we do not need to know any electrical engineering or whatever for this problem. We just want to use the known Taylor series for the exponential. So let's consider e to the minus RT over L. We have the power series x to the n over n factorial, but now we're subbing x with this minus RT over L. So we're going to have 1 minus RT over L plus RT squared over 2 factorial L squared minus RT cubed over 3 factorial times L cubed plus RT to the 4th power over 4 factorial L to the 4th power, and then this goes so on and so forth. So we can now look at that exponent, which is, or sorry, the function 1 minus e to the minus RT over L that's given in the problem. And we can rewrite this as just RT over L minus RT squared over 2 factorial L squared plus RT cubed over 3 factorial L cubed minus RT to the fourth over 4 factorial L to the fourth, on and on and on. Okay. So at this point, we have our Taylor series expansion for really the more difficult stuff. So let's just go back to our original equation, which is I equals V over R times 1 minus E to the minus RT over L. And just do some basic substitution. So this will be V. And well, V times all of this. So we'll have T over L minus RT squared over 2 factorial L squared plus R squared T cubed over 3 factorial L cubed. I'm just opening up these parentheses. Hopefully you can see that's what I'm doing with this. Okay. Now minus R cubed T to the fourth over 4 factorial L to the fourth, so on and so forth. Close our brackets. Okay, so the Taylor series about R equals 0 is specifically given as I is V times T over L minus VT squared 2L squared R plus VT cubed 6L cubed R squared minus VT to the fourth over 24L to the fourth R cubed, on and on and on. Now at R equals 0, all of these terms go away with R in them. So all we're left with is that I is approximately VT over L. We just left with this. For R, we should specify R small. Okay, so that's it really. That's as far as that's this whole problem. And I guess I jumped a step. Let me make sure. So part A just wants the Taylor series. So this is your answer for part A. This is the Taylor series, but it's about R equals 0. So we put I as VT over L. Now, part B just says deduce that I is approximately VT over L if R is small. And that's the argument I made here just from the Taylor series, that these terms all go to 0 and we're just left with this. And so like the next correction is linear in R, which would be like negative VT squared over 2L squared R. So as long as R is small, then we approximately have that I is just VT over L. Okay. So as far as this problem goes, don't get caught up in the fact that it's like a word problem, if you will, or like an application problem. We're just considering that we know what Taylor series for e to the x is, so we're going to use that to our advantage to re-express this whole thing and find a Taylor series. And that's it. So that's all the problems from this review. I know Khalid gave you another review as well, so please feel free to reach out if you have any questions and stuff before the exam.